Hi, my name is Miller Devane, and welcome to Physics 2212 Lab 5. In this lab, I drop a magnet through an aluminum pipe or an aluminum foil simulating an aluminum pipe to analyze the interactions of these two objects. The purpose of this lab is to collect data such as magnetic field, force, current from the described experiment, and to create a computational model and compare the time it takes for the magnet to fall through the pipe in the real and computational experiment. The main result was that the experimental time was 1.252 seconds and the computational time was 0.822 seconds. Concepts and formulas used are Ohm's law, Biot-Savart law, magnetic flux, Faraday's law, Newton's second and third laws, which are all shown here. Initial conditions was that the length was 0.3 meters, the width was 0.006 meters, the inner radius was 0.026 meters, the radius was 0.031 meters, and the magnetic mass was 0.025 kilograms. The system, as defined, is the magnet in the aluminum tube, and the surroundings is everything else. Assumptions that I made are that air resistance is negligible, magnetic force and gravitational forces are the only forces that are acting on the system, and the bar magnet acts as a magnetic dipole. Procedure and data. The procedure was to drop the bar magnet down an aluminum foil, which acts as a tube, and then to time how long it takes for it to reach the bottom, and repeat this for 5 trials. The 5 trials are shown on the right with the average time listed at the bottom. The computational model code shows my constants there at the top left, measurements that I made there at the bottom left, magnet values there at the top, magnetic field function, which is calculated using the formula shown there, and the magnetic flux function, which is calculated at the bottom. The continued computational model will show the magnetic force on the left, which is the force of the magnet on the ring and the force of the ring on the magnet for the total forces acting on the system. Other calculations such as d flux over dt, the ring and current, and coloring each ring according to its current. Gravitational force is shown on the right. Net force is also shown as force of gravity plus force of magnetic, and the velocity and position are shown there at the bottom right, or the calculations. So the velocity versus time graph, there's a steep decrease in slope or steep slope at the beginning of the velocity versus time graph. And this is because the F grav is greater than the F mag there, gravity and magnet, of course. And so the bar magnet will start to accelerate. In the middle, there's no slope, so F gravity is equal to F magnetic, and the bar magnet will stop accelerating and remain at a constant velocity. F gravity is greater than F mag at the end, again, so it'll accelerate as shown on the graph. The blue end is negative and the red end is positive on the far right image. Interpreting the simulation. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing opposite directions. Which color corresponds to clockwise and counterclockwise? Red is counterclockwise and blue is clockwise, and we use Lenz's law to determine this. What happens to the dynamics of the system when you flip the magnet around? It would fall in the same amount of time, but the direction of the current would flip in both. How does the total time in tube of your real world system compare to that of your computational system? And how might the computational system be made more accurate? They were similar, with the computational being a bit shorter. Adding more rings and accounting for air resistance in the simulation would make it more accurate. Does the shape of the velocity versus time plot tell you anything about the forces acting on the bar magnet? Gravitational force is greater than the magnetic force while entering and exiting the tube, but it's equal to it while inside the tube, which is shown in the constant velocity on the velocity time graph. So potential sources of error are human timing error and air resistance. Along with that, some of the assumptions are obviously not perfect, so there could have been error there as well, along with calculations. What if the resistivity of the conductor were reduced to as close as possible to zero? How would the dynamics of the falling magnet change? Ohm's law states, so the reduced resistance would increase the current, causing the magnet to fall even slower. And this is shown in Ohm's law, which is I is equal to V over R. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? It would cause there to be less rings, which would decrease the magnetic force and make the bar magnet fall faster. And that's all. Thank you.